So this problem asks us to find the electric field anywhere around some continuous line of charge given a constant charge distribution, linear charge density of lambda. Now it says assume this is an infinitely long line of charge. That's a good assumption if it is a very long line of charge, or if we're just very close to it. So the distance between our point and the line of charge is small compared to the actual length of the charge. But anyways, put that aside for right now, because for our purposes, we're going to say that this is in fact an infinitely long line of charge. Now there are different ways we can approach that. We can say, let's say we're at some point P in the middle here, and we want to find some differential charge element dq, and that's going to create a field element dE. So dE is equal to k dq over r squared, which will be the distance we are away from this. So I guess we call that x if you would like, and y down here. So this would be k dq over x squared plus y squared, and that would be itself squared. And we will also note that for every dq element we have down here, we have a dq element up there, which will create a dE down here. So the only thing that matters is the x component, because all of the y components are going to cancel out. We worked a few problems like this, so we have to put a cosine of theta term in there. So in order to find the entire electric field, we would integrate dE, and that would be the integral of k dq over x squared plus y squared, squared this term, times cosine, which would be adjacent x over the square root of x squared plus y squared to the 1/2. Now, then we have to start taking about what is dq. Well, that is lambda dx. I'm sorry, it'd actually be lambda dy because we're integrating along the y direction. So we would have to put that in there. Lambda dE equals k lambda dy over x squared plus y squared to the 3/2, and I believe there's an x in there. Yeah, the x goes in there. So if we pull out all the constant stuff, k lambda, x is constant because this is a constant distance away from this charge, and the integral is dy over x squared plus y squared, 3/2. So we worked a problem similar to this, but we ended up with, we're integrating with respect to y, so we would have a y up there. We can evaluate that integral. That we just use a u substitution, and when we find the derivative of u with respect to y, another y comes in there. We worked a few problems like that. I think there's one on the homework too. This one is way more complicated because we don't have the y here. This is a much harder integral to solve. I believe we'd have to use a trig substitution in there. I don't really want to go that route. That's kind of a difficult integral, and why not make things easier? So how are we going to make things easier? By using Gauss's law, of course. Gauss's law is going to let us solve the same problem in a much easier way. So let me just erase this stuff. I mean, let me be clear. You can solve it this way, but let's solve it the easy way if we can. And I just should mention that this is the way, this works everywhere. You can always do this kind of stuff. Gauss's law also works everywhere, but it's really only useful if you have a lot of symmetry in the problem, which we do here. We have this cylindrical symmetry. So Gauss's law says that the flux through some imaginary Gaussian surface is equal to E dot dA, the integral of E dot dA. Now this is just the definition of flux. This is not Gauss's law yet. But the flux through the Gaussian surface is equal to the charge enclosed over epsilon. Now, so what kind of Gaussian surface are we going to draw? I mean, it's imaginary, so it's just our choice. We can draw whatever we want to. But as I noted earlier, there's a lot of symmetry in this problem. This problem takes on a cylindrical symmetry. So I'm going to draw a cylinder, obviously, centered around the line of charge and given some radius r. And of course it's a cylinder, we have to give it some length L. So with the cylinder, now we have three continuous surfaces that we want to talk about. Surface 1, surface 2, and surface 3. Actually, let me define it like this. I want to be consistent with the notes. I'll call this 1, this 2, this 3. So surface 1 is the outer surface of the cylinder. Remember, the Gaussian surface is a surface, so it's like a shell. So this is a spherical shell. 1 is the round surface around the outside of the shell. 2 and 3 are the flat circular surfaces that cross through the line of charge. So looking at the flux to the Gaussian surface is the sum of the flux of 1 plus the flux of 2 plus the flux of 3, all three surfaces. But what do we note about surface 2 and surface 3? Well, let's look at surface 2. As we mentioned, when we were doing that stuff up here, only the electric field that goes directly out from the line of charge is going to count. Everything else gets canceled out. So the electric field everywhere points outward from the line of charge. And of course, it points out of the paper and into the paper on the other side too. It's hard to draw that. Where does the vector that defines the Gaussian surface, at least through 2, point? Well, I'll call this dA2. It points outward from that surface, which is perpendicular to the electric field E. Same thing down here. dA3 points downward, which is perpendicular to the electric field pointing outward from this line of charge. So what that's going to mean is if we look at the flux surface 2 of E dot dA, well, this equals the integral of EA cosine theta EA, the angle between E and A. Well, this is always 90 degrees. Theta EA equals 90 degrees, so this term equals 0, so the total flux equals 0. It's the same thing for surface 3. Surface 2 and surface 3 have the same flux, and they equal 0. So the total flux through the Gaussian surface is just the flux through surface 1, the curved surface. So the flux through the Gaussian surface, it's the flux through surface 1, E dot dA1. Well, again, that simplifies to EA cosine theta EA1. This angle here, dA1, is in the same direction as E. And over here, dA1 is in the same direction as E. So this is always 0 degrees, so this is always 1. And does E depend on anywhere around the circle? No, as long as you're at a fixed radius, the electric field is going to be the same all the way around. So this is just equal to EA. And I guess I should put A1. So EA1 equals charge enclosed over epsilon naught. What is the area of this surface? Well, it's going to be 2 pi r, which is the radius of a circle, times the length. And what is the charge enclosed? Well, that is going to be just the charge enclosed by the cylinder, remember? So that is going to be the linear charge density lambda multiplied by that length that is enclosed inside the cylinder. So that would be L. Well, the problem doesn't tell us what L is. I just threw that in the mix, and the fortunate thing is it cancels out, so we don't need to know. If I divide each side by E, that is 1 over 2 pi r lambda over epsilon naught. So go over here. E equals 1 over 2 pi epsilon naught lambda over r. That looks very close to Coulomb's constant, but what if I make this a 4? So E equals 1 over 4 pi epsilon naught lambda over r, but now I've changed my equation, so if I put a 2 up here, that fraction comes back to 1/2. So E equals 2 times Coulomb constant times the linear charge density over r, where r is the distance away from that charge. And we found the electric field. Way easier than doing this, right?